In this section, we're going to begin with a look at a new method of solving differential equations. Then we'll turn our attention to problems involving exponential growth and decay. Let's look at the solution, this new way of solving differential equations. Now, in the past, we have solved differential equations in these two forms. And notice that in these two forms, this f of x is an expression involving one variable, x. And that's true in both cases. A more general idea here is for the expression to involve more than one variable. And that's the situation we're going to look at. Now, the solution to the differential equation and the technique involved is called separation of variables. And it works like this. Suppose we have y prime equals 2x over y, and we want to solve this differential equation. Well, let's just we'll basically separate the variables, one on one side of the equation, the other on the other side, and integrate on both sides. So we would multiply on both sides by y. We'd have y prime over here, 2x over here. We integrate on both sides, and away we go. Now, the y prime dx becomes dy. So the integral of y dy is what we have here. Now, we can arrive at this point in the progression, perhaps a little faster, maybe a little bit easier, because all of this is a recognition situation. So instead of writing this, we might want to write this form. You see, we might want to use the dy dx form rather than the y prime form. And the reason for it, well, I'll show you in a minute. We have dy dx, and then we separate here. We just multiply on both sides by the dx, and we get this. So notice that in this form, we are just putting all things, all matters that involve y on one side, all matters that involve x on the other side, and that's the pattern that we're trying to accomplish. And at this point, we integrate on both sides, and away we go. Now, I have reproduced this step up here. And let's continue. The integral of y dy is y squared over 2. The integral of 2x dx is 2 times x squared over 2. The 2's go out, and we have this. And now it's a manipulation problem. And do notice that we have a constant only on one side. And we would, if we're integrating here on both sides, we would have a constant on both sides. But it's easy to see that if we have a constant here and a constant over here, that we could kick them both to one side, collect those constants, and have a new constant, you see. And so in this process, we just eliminate all of those intermediate steps and just put a constant on one side. And notice I'm putting a subscripted 1 here, because in the process of manipulation, it may turn out to where this constant has a constant multiple or something like that, or it changes its form, but it's still constant. And in that circumstance, we would want to eventually, at the bottom of the problem, make the replacement as simply c. So we start out with a c subscript 1 here. Okay, at any rate, we can think of y squared over 2 as 1/2 y squared. We'll multiply through by 2 to clear this 1/2, and we get this. There are other manipulative forms, but an important idea here is that the 2c sub 1 is a constant, and so we'll replace that with simply c. Here's another one. We're just practicing this idea. Y prime is x times 1 plus y. Now, I suggest that we express the y prime as dy over dx very early in this process. You don't have to do this, but I think it's a little bit easier. It's a little bit easier for me to see the pattern if I use this kind of manipulation technique. All right, at any rate, I'm going to multiply on both sides by dx, and I would get this. And I'm also, at the same time, dividing on both sides by 1 plus y. So this comes over here, the dx goes over there, and here we are in the form that we need. That is, we have all matters concerning y on one side, all matters concerning x on the other side. Now, we want to put this into again, into a pattern where we can easily see the integration. And that's why I have separated this as 1 over 1 plus y dy. And then over here I've just brought down. But just for me personally, I can recognize the integration easier in this form than I can in that form. And that's what you might consider as well. You might like this, and that's perfectly all right. But put it into a form that you're familiar with, and then integrate on both sides, and it becomes pretty easy. So the integral of 1 over 1 plus y dy is natural log of 1 plus y. And on the right, this is x squared over 2, and we add the constant. Now let's come up here. We have x squared over 2. That's 1/2 x squared. We come up here and continue the problem. Now we're sort of trying to solve this for y. We didn't exactly solve for y in the previous problem, but it would be kind of nice if we could solve this for y. And it's pretty easy in this problem. Now we go from the natural log form here into the exponential form. Now we understand that it's base to that exponent, so it's e to that exponent set equal to 1 plus y. So 1 plus y is equal to e to this as an exponent. And now it's all manipulation. Now e to this sum, you see, in the exponential world, adding exponents corresponds to multiplying like bases. So we can write this as e to this exponent times e to that exponent. You see, it's really this. And we can do this very quickly if we do this a few times and we notice the same kind of pattern. But for right now, I want to make sure we understand how I'm getting this from that. Okay, now this e to the c subscript 1 is a constant raised to a constant, so this is just a constant. So I'm replacing this with c and writing it to the left as a coefficient. And now y then is this minus 1, and we're done. Now, we're going to move now into the exponential growth and decay type of problem. The classical model for exponential growth and decay is this one. It's y equals ce to the kt power. Now, the elements here, the c is a constant standing for the initial value or the initial amount of substance, or the initial amount of population if we're talking about population growth. The k value is a proportional constant. It's in there to alter the rate of growth or to determine the rate of growth or decay in the problem that we're talking about. T stands for time, and y is the amount of population or the amount of radioactive material if we're talking about radioactive decay, but it's the amount of substance that we have or the amount of population we have after a certain period of time. Okay, in this kind of model, when k is positive, it means we have a growth pattern. That is, we have a constantly increasing kind of function. And when k is negative, we have a constantly decreasing type of function, and that's what happens in the decay models. Now, all of these, this kind of classical model often emerges from some information on rate of growth, rate of growth. And it's kind of important to understand that because in textbooks, a lot of times you'll see this model used with the c and the k filled in. Those constants are given to us. Well, how did this model emerge? Well, it emerged probably because some scientist has done some research in terms of counting population after a certain amount of time or something like that, but just with basic information on rate of growth, you see, we can use our calculus techniques to generate this kind of model. Suppose we want to write and solve the differential equation corresponding with this statement. It says the rate of change of p with respect to t is proportional to 10 minus t. Now, in writing the differential equation, we need to understand that the idea of rate, as soon as we see the notion of rate, rate is related to slope, slope is related to derivative, derivative is related to rate. I mean, all three of those ideas just churn around and are close cousins with one another. So when we see rate of change in a problem, we're thinking derivative. And so it's the rate of change of p means p prime, the derivative of p. Now, it's the derivative of p with respect to t is proportional to. Now, as soon as we see proportion, we say, gee, if a is proportional to b, it implies the existence of a constant k such that a is equal to k times b. So we have here a situation where this rate of change of p, p prime, is proportional to this expression. It means we have p prime equals k times this expression. So it's p prime equals k times expression. All right, this is the differential equation that we want to solve. Now, to solve it, we go through the process that we were talking about earlier. Basically, although we don't need to separate variables so very much here, but P prime is the derivative of P with respect to T. Now remember, the respect to T is where this comes in, or comes from. So dP over dt, and now multiply dt on both sides, we get this, and integrate on both sides, and away we go. Now there are really a couple of ways that we can approach this, this integration on both sides, particularly over here. Let's look at one way. Now thinking about on this side, I've just extracted the k to the left of the integration symbol. Now some folks will want to do this all in one or two steps and sort of skip steps with it. I'm not going to skip any steps, and I encourage you to be very careful about that. The tendency is to want to, because you can kind of see through one or two steps here, but I encourage you to, just like in algebra, you want to always be writing, and that way you'll minimize the number of mistakes that you make. Well, at any rate, the k comes out, and I'm thinking of the integral of 10 minus t dt, and it's the integral of the 10 minus the integral of the t part, you see. And these are very simple integration techniques that we can use. The integral of dp is simply p, and in the brackets here we have the integral of 10 is 10t, the integral of t is t squared over 2, and then we have our constant. Now, at this point, all we need to do is distribute the k through this binomial, so we have 10kt minus 1/2 t squared plus our constant. Now, I said there were two ways to do it. Some folks will look at this, and instead of thinking of sort of distributing the idea of integration through the binomial, they'll think, well, let's attack the problem just as it is. We have the integral of something we might think of as a u, you see, and the integral of the u part, and this is the other way to do it. I've duplicated this step up here, and we're just thinking about it as the idea of the integral of u. And the integral of u is the notion of u squared over 2 times u prime. And so here's the u, and it's u squared over 2 times the derivative of this would be -1. And now when the smoke clears on this a little bit, well, let's see, we've got the -1, the 2, we yank those out, we have -k over 2 times 10 minus t all squared plus our constant. Now we could leave the problem in this form, but you know, it doesn't look a great deal like the form that we had before. And it doesn't necessarily mean that it isn't the same thing that we had before, it just looks different. And if you were looking in the back of your textbook at the answer to this problem, you might see it in this form, you might see it in the other form, and you might think, which one is right? Well, it turns out that we can manipulate from one form to the other, particularly from this form to the other. If we square the binomial, we get this trinomial, and if we multiply by -k over 2 in this trinomial, we get -50k plus 10kt minus 1/2, and so on. All right, now these are terms that were in the other form, and notice that this is a constant and this is a constant. We just put those two constants together for one single c, and this expression is the same as the one before. Well, the situation that we began with here was a situation, it started with the rate of change of p, sort of presumably thinking population, with respect to t, time, is proportional to 10 minus t. Okay, is proportional to some function of t. Well, actually, when you think of population growth problems, the classic way that the rate of growth changes is more according to the amount of population rather than an elapse of time. That is, the rate of growth of a population at a point in time is related to the amount of population and not so much related to an elapse of time. Now, it is true that the population is a function of time, you see, but let me put that in this kind of context. Think about a model for, and we're going to write a differential equation here, but we want to talk about a model that is the rate of growth is proportional, the rate of growth of a population is proportional to the population size itself. So it would be more like y prime. I could have used p here, but I'm using y for the familiarity of the xy kind of notation that we're more familiar with. But y prime is proportional to y. You see, that's the classic kind of relationship that we're talking about in this kind of model. Now, let's go ahead and I've written a differential equation. Let's go ahead and solve it here just for practice. The y prime is dy over dt. Now, remember, y is a function of t. So this is dy over dt. So we have dy over y. I've moved the y over here. The dt I've moved over there. All right, I've just separated the ideas, all matters involving the y and the t, to separate sides of the equation. Now the dy over y, I'm thinking of this as 1 over y dy for integration purposes. And this I just bring down, integrating on both sides. The integral of 1 over y dy is ln y. And the integral of k dt is kt. And then we add the constant on one side. All right, I've brought this step up over here, and let's continue. Now we're solving for y, and we know we have from the logarithmic form, we go into the exponential form, base exponent equals y. So y equals this base to that exponent. And now, as we saw earlier, this can be written as e to the kt times e to the c sub 1. And this is nothing but a constant. So it is y equals ce to the kt power, the classic model for exponential growth and decay. We're going to look at a couple of problems involving exponential growth now. Before we do, though, I want to say again something that I said before. I think it's rather important that we understand how the exponential growth and decay model emerges. And it starts from the idea that the rate of growth of a population is proportional to the population size, not proportional to time. It's the idea that if you have a population of rabbits and you want to know the rate of growth of that population, doesn't it stand to reason that the rate of growth, the number of extra rabbits per month, let's say, or something like that, is related more to how many rabbits are in the original population, or how many are in the population at the time that you're measuring the rate of growth. If you have a population of 10,000 rabbits, certainly the rate of growth is much higher than if you have a population of 5. You see, something like that. So it's the idea that the rate of growth is proportional to the population size and not so much related to time. And that's what jumpstarts the whole idea for this growth and decay model. Anyway, here's a problem involving the situation. We're not going to have to integrate here, but we're going to have to do some manipulation. We're talking about fruit flies, and fruit flies are an ideal example for this kind of model because they tend to multiply like crazy. At any rate, we start with, let's say, 50 fruit flies, and after 2 days there are 150 fruit flies, and after 5 days we would like to know how many we're going to have. Well, we start with our basic model, and the key here, the elements that we're looking for are the values of C and K. And we're just going to use information about what we start with and what we have after 2 days to figure out the values for C and K. Here's how it goes. So we start with our basic model, and then we replace within it the information that we know about the starting. Now, at the start of our experiment, that means no time has elapsed. So when t is 0, we have 50 flies. Now y stands for the number of flies in the population, the number of items in our population after a certain period of time. So we replace for those two. We have y is 50 then, t is 0, and now we can easily solve for c. Now notice, because 0 times k is 0, e to the 0 power is 1, so c then is 50. Now if we know that c is 50, we can put 50 back in here, and then we have y equals 50 e to the kt power. Now we use the information about the number of flies that we had at the end of 2 days. So we replace t with 2 and y with 150, and then we're going to go through and solve for k. All right, dividing on both sides by 50, and then bringing this down. This is 150 over 50 is 3. We take the natural log on both sides, so we have natural log of 3 on the left is the natural log of this. The 2k becomes the coefficient of ln e. Now, in the future, when we go through this process, we know that ln e is simply 1, and we won't even write the ln e. If we have ln e to some exponent, we'll just write the exponent, okay, from here on out. But at any rate, we're solving for k, so we divide on both sides by 2. We find k to be ln 3 over 2, which is approximately 0.5493. Now, we have the value of c, we have the value of k, so our model now becomes y equals 50 e to the 0.5493 t power. And now, here's our fundamental model for determining the number of fruit flies after any number of days. For example, if we want to find the number after 5 days, replace t with 5, punch the calculator, we find the number of flies to be approximately 780. Now, one of the key elements in this problem that made it relatively easy was the idea that we knew how many flies we started with. You see, because when t is 0, the kt part becomes 0, e to the kt becomes 1, things drop out rather nicely and we find the value of c just like that. Well, suppose we have a situation, same idea now with fruit flies, but the initial population of flies is not known to us. But we do know that after 2 days we have 100 flies and after 4 days we have 300 flies. And we just want to know the initial population. Well, we start the same way. It's fundamentally the same idea. We just begin to manipulate our basic growth and decay model. Now, there are a lot of right ways to do this, so don't assume that because you see me do it one way here that it's the only way to work the problem. But here is a way to proceed. We start with the basic model for exponential growth or decay, and we put in information about one of these days. Well, I've put in the information about t being 2 corresponding with 100 flies. So y is 100 when t is 2. Now I've got a choice here. I can solve this for c or for k. It's pretty easy to solve for c. C then is 100 divided by e to the 2k, or c is 100 e to the negative 2k. All right, now with this information, what we're going to do is take this information about c and pop it into a relationship having to do with this 4-day information. Here's how it goes. We start with the basic model again. We put in the information about what happens after 4 days. That is, when t is 4, y is 300. Okay, here's the model for the 4-day period. Then we have information about c. We have a substitution for c. c is 100 e to the negative 2k. Just pop that in here and then let the smoke clear on this and solve for k. That's what we're doing. Let's see, e to the negative 2k times e to the 4k. 4k minus 2k is 2k. Divide on both sides by 100. 300 divided by 100, that's 3. So we have 3 is equal to e to the 2k. So e to the 2k is 3. Take the natural log on both sides. This becomes 2k equals ln 3. K then is ln 3 over 2. K is 0.5493. Now this happens to be the same value of k from the previous problem, but it isn't the case that this is the value of k anytime we're talking about fruit flies. It just so happens that it was set up to be the same amount. All right, at any rate, with this value of k now, we have the ability to go back and find c. Now c is what we're looking for in the first place. And we solved for c in our first model, but c was solved in terms of k. Now we know k, so we can easily find c. You see, c is the initial quantity in all of these kinds of problems. And and it is the initial quantity in all of these kinds of problems because if you let t be 0 in the basic model, then you get y equals c, you see. So at any rate, it's the initial value. C is 100 e to the negative 2k from back over there, and replacing k with the value we just found for it, we find c to be approximately 33 flies. So we started with 33 flies. A classic calculation in problems like this is doubling time. Now, we actually performed the task of finding doubling time when we were talking about an investment earlier. It was a model similar to this, having to do with continuous compounding of interest on an investment. And the process of finding the doubling idea is very much the same. Here, if we want the doubling time for these fruit flies, then we start with our model. Now, we have determined that the initial number of flies is 33, and we have the value of K that we determined also to be 0.5493. So here's our fundamental model. Now, doubling time means that we want the T value when Y is double the initial number. So Y is 66 and the 33. Now, we really don't need, in calculating doubling time, as we may remember from the model involving continuous compounding, we really don't need to know the initial quantity. It doesn't make any difference whether we know that we started with 33 flies or we have 3,000 flies to start with. The doubling time is going to be the same. If we didn't know the value of the C, then what we would use for Y is just 2C. You see, double whatever C is. So at any rate, the point is you don't really have to know this value in order to perform this task. You do, however, have to know the value of K. At any rate, we have dividing by 33 on both sides, we get 2 on the left, and now we're solving for T. We take the natural log on both sides, and so we have ln2 equals coefficient. This becomes the coefficient, and now we're solving for T, so we divide by the coefficient of T. So T is ln2 over this 0.5493, and that's approximately 1.3 days as the doubling time for the population of fruit flies. This next problem involves radioactive decay. We still use the exponential model that we were using before. Now, radioactive material is quite nasty because of two characteristics. One characteristic is that it's highly toxic. The other characteristic is that it stays around an awfully long time. For example, radioactive radium has a half-life of about 1,620 years. Now, half-life means that if we started with a pound of this material, then we would have a half pound of it 1,620 years later. And then after another 1,620 years, we'd have half of that. So we'd still have a quarter pound left after twice this amount of time. Anyway, what percent of a given amount remains after 100 years? Now, it says of a given amount. We're not told how much we have to start with, but it really doesn't make any difference. We will still be able to represent the percent of that given amount after 100 years. We start with our exponential model, our classic model, and we put in information that we know. Now, Y is the amount of material after a certain period of time. C is the amount that we start with. And if C is what we start with, and we have information about half-life, then half of C remains after a time of 1,620 years has elapsed. Now notice that what we're doing, we're just plugging in information that we know, and the C's will go out nicely, and we'll take the natural log on both sides in an effort to calculate K. All right, so we have natural log of 0.5, or 1/2, is natural log of e to the k times 1620. So let's see, the 1620k becomes the coefficient of ln e. Ln e goes out, so we have this, then we divide on both sides by 1620 to find k to be ln 0.5 over 1620, or approximately this very long-winded decimal. I think I'd rather use this value in the model rather than this value. This is an awful lot of digits to write, plus this is more accurate. That's an approximation, even though it's a very close approximation. It's an approximation, and this is simply more exact. By the way, there are a couple of ways of representing it. This ln 0.5 could be represented differently. I'm going to represent it like this, but I want you to know that there are some variations that are possible with this. Let me show you. I'm going to see if I can find an open space here. I have a little bit right here. ln 0.5 is ln 1/2 is ln 1 minus ln 2. ln 1, 0. So we could represent ln 0.5 as negative ln2. Means the same thing, so it would be the same value. But anyway, there are different forms. If you saw one of these and then the other, you might think something was wrong, but no, they are equivalent to one another. All right, now let's go back to the model and pop in this value of k that we just determined and see where that leads us. We have y equals ce to the kt. Here's the k that we just determined. Now we're talking about the percent of material that remains after 100 years. So take the model and replace t with 100 and then e to the ln 0.5 over 1620 times 100. This is just some sort of constant. And so when we calculate that, it turns out to be approximately 0.958. I should put approximately equal to. But at any rate, what this is saying now is that the amount of material after 100 years is this fraction or this part of the initial amount of material. So we can say then that y, the amount of material after 100 years, is 95.8% of the amount of starting material, and that's the amount that remains after 100 years. Quite a lot of it, as you can see. That's what makes it so awful. Let's look at another kind of problem. This one has to do with Newton's law of cooling. And Newton's law of cooling says this: the rate of change in temperature of an object is proportional to the difference between the object's temperature and the temperature of the surrounding medium. And that just kind of makes sense if we think just sort of intuitively of what this is saying. It's saying that if something is really, really hot and it gets into an environment that's really, really cold by comparison, then the rate of change is going to be greater than if it is very near the temperature of the surrounding area. If it's not very hot and it comes into an environment that's not very cold, then the rate of change isn't going to be very great. That's all it's saying. Okay, so from our calculus perspective, it is the derivative of the temperature of the object with respect to time. Now t, the temperature of the object, is well, we could write the big T as a function of time. Temperature changes with time. So it is time as temperature is a function of time. So when we talk about rate of change in temperature, it's dt over d time. And it's k, that's proportionality idea, implies a constant k. And it's k times that difference, the difference between the temperature of the object and the temperature of the surroundings. Okay, let's consider a problem. An object at 1500 degrees Fahrenheit is placed in an environment of 90 degrees Fahrenheit. 1 hour later, the object is 1120 degrees Fahrenheit. What is the temperature of the object 5 hours after initial exposure? Now, there are a couple of things, a couple of aspects of this problem that we're going to look at. I want to explain to you, though, that although Newton's law of cooling says that the object is changing temperature, gee, if we start with an object that's 1500 degrees Fahrenheit and put it into any kind of environment, I'll bet the environment's temperature would change as well. I mean, we're assuming here that the temperature of the environment is staying relatively constant. Let's assume that we're putting this thing outside, outside will change in temperature if you're in close proximity with something that's 1500 degrees, however. But those matters, we'll make the assumption that the surroundings will stay at 90 degrees. Although it's a little bit unrealistic to think that that actually would happen, particularly if the outside environment is a confined area. All right, let's go on with our problem. All right, we're going to start with the idea of the change in temperature with respect to time, that rate of change in temperature of the object with respect to time is proportional to, that is, there's a k, is proportional to the difference between the object's temperature and the temperature of the surrounding area. Now this temperature of the surrounding area we're assuming stays constant, and this is a variable. This changes as time goes on, and so this is our model that we're going to proceed with. All right, we're going to try to put all matters concerning uppercase T on one side and all matters concerning lowercase t on the other side. So here I'm dividing on both sides by the t minus 90, and I'm multiplying on both sides by the dt. So I have d uppercase T over t minus 90 equals k dt. Now on the left I'm considering this as 1 over t minus 90 dt. For integration purposes, I can see it a little easier. I can see the integration process a little more easily if I write it like this. All right, so this side then becomes the natural log of t minus 90. This side becomes kt plus a constant. So we have this as our model that we're working with from here. Now I've put this asterisk here to remind me to mention something. I'm going through this problem and I'm using a little nuance, a little change in the way that we would normally view a problem like this. At this point in the problem, algebraically, we could solve this easily for t. After all, the exponential form would be t minus 90 equals e to this exponent. And then we would add 90 on both sides, and we would have something like t equals CE to the KT plus 90. Okay. But we don't have to do that. We can stay in this form and begin to make our substitutions. It's at this point in a problem like this where we're trying to identify the value of C and the value of K. And we do that by making our substitutions of initial value and other such things. And in this problem we have the initial information about the temperature of the object. We have also information about the temperature of the object after 1 hour. So let's see, using a t of 0, the initial temperature of the object, that means no time has elapsed. The temperature of the object is 1500 degrees, very, very, very hot. So if a t is 0 and the uppercase T is 1500, then ln, this difference, ln 1410, is equal to C. This term goes out. So with the information about the value of C, we put that into our model right here, and then we can substitute for the other information. I've reproduced this up here using the C of ln 1410. Now, again, at this point, we could solve this for T. You see, and put it into that more traditional model that we talked about earlier, or we can use the information about the temperature of the object after 1 hour, pop it into here, T is 1, and the temperature of the object is 1120, then we would have this. Now, the 1120 minus 90 is 1030, and we subtract ln 1410 on both sides, so we get this. Now, ln 1030 minus ln 1410 is ln 1030 over 1410. The zeros can be eliminated, so we have this. Now, once again, we could approximate this as some kind of long decimal, presumably, and write it like that, or we can leave it in the more exact form like this. I'm going to leave it like this for our purposes. All right, I'm going to replace K in our model above with ln 103 over 141. So here then becomes our model. And at this point we can use this to calculate the temperature of the object at any point in time in the future. And our problem requested that we find the temperature of the object after 5 hours. So we let the T for time be replaced with 5, and we evaluate. So this side becomes just punching the calculator. This becomes approximately 5.68119, and now we go into the exponential form. The t minus 90 is equal to e to this exponent, and then evaluating this and adding 90, we find the temperature of the object after 5 hours to be approximately 383.3 degrees Fahrenheit. Still pretty hot.